Hi. Now, we will discuss the protection and repair of wind turbine blades, and also reserves and possibilities for their improvement. We will discuss general tendencies of wind turbine blade degradation, mechanisms of leading-edge erosion of blades, computational models, common repair approaches and technologies. Everybody saw this graph, and everybody knows that the wind turbine became larger and larger over last decades. But another interesting aspect of the wind turbine design is that they are installed in less and less maintenance-friendly locations. Wind turbines are installed offshore, at some distance from coast, in North Sea, in monsoon areas. Let us make a comparison. An airplane is inspected before each flight, and a maintenance team is there, in every airport. To repair your car, you just make a phone call, and wait half an hour. But repairing a wind turbine, located in North Sea, many kilometers from the coast, means considerable efforts. Wind turbine blades are subject to complex loading, including random cyclic mechanical loading, environmental wear, rain, sand and contaminants-caused erosion, lightning strikes, thermal cycling, fatigue, moisture intrusion, and foreign object impact. How often do wind turbine blades need a repair? In fact, surprisingly often. In the paper by Carroll and colleagues, the average failure rate for wind turbines is 8.3 failures per turbine per year, including 6.2 minor repairs. For blades, they observed 0.46 repairs per year. We at DTU carried out a survey among different companies on frequency of damage mechanisms. It was reported that first damage event is observed after 1 to 3 years after installation of wind turbines. Repair of wind turbine blades is quite expensive. Let us list here some numbers. Maintenance of a wind turbine blade costs 2 to 3,000 euro per turbines per year onshore, and 2 to 3 times more offshore. Generally, operation and maintenance costs can take 25% of the total levelized cost per kilowatt hour, produced over the lifetime of the turbine. But why the wind turbine blades need repair? What are the main mechanisms of blade degradation? On this slide, you see some common degradation mechanism of blades. Which degradation mechanisms are most common? Carroll and colleagues reported that minor repair are required in average 0.45 times per year per turbine. Major repair are required in average 0.01 times per year. Again, we at DTU carried out the worldwide survey, in collaboration with Indian National Institute of Wind Energy. The most common blade degradation mechanism is the leading-edge erosion, both in Europe and in Asia. How the leading-edge erosion of wind turbine blades takes place. Blades are rotating, with high velocity, under rain, hail, sun. Rain droplets hit the leading edge, with velocity from 50 meters per second and higher, day after day, year after year. Stress waves from these small impacts propagate in the blade materials, or reflected on interfaces, interact with inclusions and other materials. Polymer chains in the blade material are compressed, and deformed. After several millions of such hits, the first microscopic crack is formed, which starts to grow, due to moisture, loading. Rain droplet impacts. We at DTU carried out detailed microscopy studies of eroded blades. Samples from eroded blades were cut, and scanning electron microscopy and X-ray studies were carried out. The experiments were followed by computational modeling. We observed that the erosion was always triggered by local manufacturing defects, in the places where the coatings had large voids, or inclusions with weaker interfaces, the erosion started. Here, you see the micrographs and computational models of the coated composite samples, subject to rain droplet impact. It can be seen that the areas of high stress concentration, near voids, are exactly the areas where the damage was observed. A computational model of rain erosion includes usually several steps. Rain scenario, and defining of the time and spatial distribution of droplet impacts, fluid impact model, and the stress wave propagation analysis. Damage initiation and fatigue analysis. Coating optimization. We at DTU carried out a number of computational studies of the erosion of wind turbine blades. Computational model of rain droplet hitting the blade surface was developed, based in the smooth particle hydrodynamics method. The effect of the droplet impact speed was investigated. It was observed that peak stress in the coating increases with increasing the impact speed. An increase in the droplet velocity from 50 to 100 meters per second leads to the 3 times higher peak stress. Next, we carried out parameter studies. The effects of droplet shape and impact direction on the stress field were investigated. It was observed that normal droplet impact creates highest local stresses as compared to oblique impact. Droplet's shape has a strong influence on the stress field, and, therefore, on the lifetime of coating. Ellipsoidal, compressed droplets lead to 15% higher peak stresses. Practically, it means that the common models underestimate the stresses in coatings. Further, void effect was studied. Even small voids in a coating drastically reduce its erosion resistance. Further, surface effects on the erosion were studied. In particular, surface roughness, and the availability of liquid film. It was observed that the rough surface increases the stress localization, leading to higher surface stresses close to the impact point. The wet surface reduces the stresses in the coating by 40–50%. The water film acts as additional protective layer. Then, stress waves in multilayered coatings under liquid impact were simulated. We compared homogeneous coatings, and coatings with stiff layer on a soft sublayer, and those with soft layer on a stiff sublayer. It was observed that the multilayered coating with upper soft layer show lowest stresses. In order to estimate the erosion quantitatively, fatigue model of material degradation under random multiple rain droplet impacts was developed. For damage modeling, multi-axial damage model was used. The model together with the raindrop impact simulations allowed to predict the local erosion damage distribution. Here, you can see the damage distribution on the blade surface observed in the simulations. On the basis of our investigations, one can formulate some directions of improvement of polymer leading-edge protection coatings. First, one should enhance the manufacturing quality of coatings, prevent void formation, and ensure good attachment of particles to the matrix. Enhance the damping properties of the coatings, use multi-layer coatings with upper soft layer, prevent surface roughness. Recently, we at DTU organized 2 symposia on leading-edge erosion of wind turbine blades. At the symposia, many world-leading specialists presented results of their studies, how to prevent leading-edge erosion. Some interesting ideas were formulated. Let us list some very promising ideas. Erosion-safe mode control, as proposed by Charlotte Bay-Hossiger and colleagues. It proposes to reduce tip speed during heavy rain conditions. Metallic anti-erosion coatings, which are developed by British Ore Catapult, can potentially ensure full lifetime blade protection. Nanoparticle engineered coatings, for instance, with graphene, can ensure 70% enhanced lifetime of coatings. Better adhesion of coatings should prevent their delamination. There are several concepts, how to prevent the blade erosion, and many groups work on them. We expect to see new results, in coming months, and years. Still, someday a wind turbine blade can be damaged, even if it is equipped with new highly durable protection. Further, there are hundreds of thousands of older wind turbines installed in previous decades. How to repair wind turbine blades, if they are damaged. In our survey, we collected information about typical inspection and maintenance strategies of the wind farm owners. The most common approach is still time-based maintenance. It means regular inspections. The repair is carried out most often by in-house teams, or wind turbine manufacturers. The algorithm of blade repair, as described by Lecu and Vianis, includes inspection, design of repair scheme, removal of damaged region, and attachment repair parts, post-repair inspection and documentation. The blade defects can be grouped in 3 categories. Surface defects, like erosion. Non-structural, matrix cracks, debonding. Structural damage with damaged fibers. Correspondingly, different repair techniques are used. Protective shells, paints, coatings for erosion. Filling and sealing, injection for matrix cracks. Scarf repair for structural cracks. Dr. Rick Hesselhurst identified 4 different repair zones of wind turbine blades, with different requirements toward aerodynamic and structural repair. Repair procedure includes removal of damaged region, surface preparation, attachment, and bonding a patch to the parent laminate. The patch can be applied as soft or hard patch. Soft path is co-cured together with the adhesive at the same time, while a hard patch is pre-manufactured in mold. An imperfect attachment, voids in adhesives, suboptimal patch design can lead to the early degradation of the repaired structure. To analyze the stress field in the repaired laminate, we developed a Python code, which automatically generates computational models of the repaired system. The model includes coating, scarf, adhesive, and laminate with several anisotropic layers. The parameters of the model, as thickness of the layers, of coatings, properties, can be easily modified. The computational models allows the analysis of the effect of the scarf geometry, scarf angle, adhesive thickness in the stress and deformation of the repaired structure. A number of computational studies were carried out. One observation is that the most dangerous area in the adhesive is close to the upper part, coating. Further, we studied the effect of the adhesive thickness and scarf angle. It was observed that the higher scarf angle leads to higher stress concentration both in the adhesive and in repaired composite. The model was validated by comparison with simplified analytical Voigt-type model. The computational studies also demonstrated that soft adhesives create additional stresses in the system, as compared to stiff adhesives. In order to analyze the effect of voids, we used the submodeling techniques. It means that a small element is placed in the adhesive and assigned various structures. In this way, the effect of its structure of adhesive on the stress field is studied. As expected, the voids in adhesive create drastic local increase of local stresses. Thus, we can say that voids in the adhesives, especially in the upper part, should be prevented. The choice of adhesives for the blade repair is not infinite. Mainly, 3 groups of polymers are used, or considered, for blade repair: epoxies, quite strong, and usable in harsh environments; urethanes, highly variable; and methacrylates, with quick curing, and good fatigue life. The main challenge of optimizing repair technology is to satisfy both requirements of lower costs and higher quality. The costs of repair depend on the time and labor necessary, and on downtimes of the wind turbines caused by repair. The quality of repair depends on clear procedure and guidelines, good training, and reliability of used materials and procedures. Thus, the strategy to the optimization and reducing costs of blade maintenance should include better and quick damage identification, optimization of used adhesives to ensure quick curing, and no defects, improved adhesion, improved scarf and shell design, clear guidelines. Let us summarize our observations. Requirements to the wind turbine blades are quite high as compared to other structures. Leading edge erosion is the most commonly observed damage mechanism of wind turbine blades. Several solutions for preventing the erosion and blade protection are under development now. Computational modeling is a promising tool for predicting and optimizing the wind turbine blade protection and repair technologies. Here, you can see the list of our publications in this area. Feel free to drop me a line if you need some of them. We are grateful to the Innovation Foundation of Denmark and to the Danita Foundation for the support in the framework of Duraledge and Maintainergy projects. Thank you very much for your attention.